And we have the bottom-up assembly, which is a bit more the chemistry approach, the molecular nanoscience. It also includes the controlled defects, and in my particular case, my interest being quantum surface science. And so let's look at what comes out of this. We've decided as a group that in the core of quantum nanoscience, or at least of quantum coherent nanoscience, is the goal to utilize quantum coherent functionality. And that's really what this field is about, and that's what makes this field interesting. But in order to do this, we have a large area around it that includes the development of new research tools, of course, the device application and device fabrication, basic science explorations of these quantum systems, and of course, quantum materials. And so we believe that at the core of quantum nanoscience lies this field of quantum coherent functionality, which includes quantum sensing, quantum computation, quantum simulation, and hopefully many other new things that we haven't even thought about yet, right? And quantum science itself is a broader field that involves things like quantum materials. Now, of course, in my center here, we don't do all of these things. We focus really on the tool development and the exploring of the quantum states in order to go more towards the quantum coherent functionality. And that means for our team in particular that we are focused on surface science. So we like to do things on very clean surfaces, as I'll show you in the following, and also focus on atomically precise assembly so that we don't have to deal with any defects. We know exactly where each atom is. And so this, maybe the best term for this is quantum surface science. And on the quantum side, we deal with superposition and quantum coherence, not so much yet with entanglement or the fine details of the quantum measurement. Okay, so to make this a little bit more concrete, we're dealing with materials and with measurement techniques. And on the materials, we have an effort in point defects, which many of you are familiar with, such as nitrogen vacancy center in diamond. But the core that I will talk about today relies on atoms on surfaces, and in particular the scanning tunneling microscopy work for atoms on surfaces. But we also have an interesting effort in designing and utilizing molecules such as this endohydrofullerene, which has interesting spin properties because of its core that synthetic chemists can put inside there. On the measurement side, after we know what our system is, we focus on the discrete energy levels, the quantized energy levels of a spin system, here characterized by a 5-level system, so a spin 2 system. We then utilize these spin systems for CW electron spin resonance. Here an example from an ensemble averaging technique. These are nitrogen defects in a diamond crystal measured in a home-built spectrometer, and then in the end go towards pulsed ESR in order to do quantum state control and maybe in the future develop qubits of these systems. So this is kind of the broad outline of what we do here in Seoul, and the talk today will focus on the materials of atoms on surfaces. I will start giving you an idea of scanning tunneling microscopy, then focus on how we can measure these discrete energy levels and how we can maybe control these energy levels, and then focus on CW and pulsed electron spin resonance. Now, the STM has a long history by now. It was invented by the two pioneers, Heini Rohrer and Gerd Binnig at the IBM Research Lab in Zurich in the very early 1980s. And the concept is very simple. We make a needle that is atomically sharp, that we bring close to a surface, for example, a metallic surface. And if we keep this distance very small, then a tunnel current can flow between the tip and the surface. And this current is extremely sensitive to the distance between the tip and the surface, and therefore can be used to image the surface with atomic scale spatial resolution. And so we measure this tunnel current, which is typically in the order of picoamps, and the voltages are maybe millivolts to volts. And then we scan this tip along the surface, keep a constant distance from the surface, and do this line by line, which then allows us to take an image of the surface. And here is a picture of the original one that Gerd Binnig and Heini Rohrer took in the very early 1980s of the famous silicon 7x7 reconstruction on a silicon 111 surface. And that answered a long-standing question in surface science on what is the atomic arrangement of these silicon atoms. And in the end, they showed that they can get atomic scale spatial resolution, as you can see here in the lower right. This is more modern images of the same surface. It's a beautiful image, but it shows you that STM can give atomic scale spatial resolution. Now here's a picture of an actual STM, one that we were just building It's the bottom part of a dilution refrigerator. It sits in a 10 millikelvin dilution fridge system. And what you see here is the STM tip. It's attached to a small coaxial cable that then goes to a semi-rigid coaxial cable to get high frequencies down there. And you see here in this area, this is where the sample would sit. There's currently no sample inserted. And this entire part of which we call the STM scan head sits in ultra high vacuum to be very, very clean. It's going down to low temperature in this particular microscope, 10 millikelvin up to 30 Kelvin, and has 2-axis magnetic field, so a vector magnetic field, because for us very often, not only the magnitude of the magnetic field is important, but also the direction of the magnetic field. Right? This then sits here in the bottom of a door, has superconducting magnets around it, and in this particular case, a temperature of down to 10 millikelvin. So these are nowadays, I guess, fancy tools, but you can still do a lot of things with home-built systems. Okay, so first step, we want to image something. Here is maybe one of the more beautiful STM images, which many people do to start off with the systems with. This is a gold surface, again, a 111 particular surface of gold at a temperature of 10 Kelvin, a relatively large area of 200 nanometers by 200 nanometers. That is about 1 million atoms in the surface layer of this gold here. And you see two characteristic features. One, you see this very large looking feature here. This is an atomic step on the surface. So here the gold is one layer thicker. So this is a staircase that is one atomic layer high. And of course, you also see this pattern here, which is called the herringbone reconstruction. This is just a surface reconstruction of the gold 111 surface. Has to do with the stacking order here, gives beautiful patterns. So STM allows you to look at surfaces with atomic scale spatial resolution if you make your images smaller. Now, let's take the next step. We want to look at spins. We want to get towards the quantum coherent control of spins on surfaces. And so in order to do this, we take magnetic atoms and we put these magnetic atoms on a surface that is not just a bare metal, but also includes a thin insulating layer in order to bring the spin a little bit away from the conduction electrons of the metal. If it is a spin 1/2 and we apply an external magnetic field, then we get the Zeeman splitting. We have two discrete energy levels, the ground state here and the first excited state here, and they are split by the Zeeman energy, which in the end only contains the G factor and the external magnetic field. Now here's an example of such an insulator. This is a slightly complicated image of 100 nanometer by 100 nanometer image of a film of magnesium oxide on silver. And you see two particular regions here. You see here, this area that is bare silver, and that is really nice for us because we can crash our tip into the bare silver and use this to shape the end of our tip and make it atomically sharp. And then we have regions like here, for example, where we have a double layer of MgO. We can also grow thicker MgO films, so you can choose to have 2, 3, 4, or 5 layers and still be using STM to tunnel on those. Now, I want to start with introducing iron on this particular surface. So the iron likes to sit on the oxygen binding site. The oxygen binding site on MgO is a twofold negatively charged binding site. Around that, you also have positively charged magnesium atoms. And so you have a ligand field here that is slightly complicated, has negative charge below and positive charge in a fourfold symmetry around it. Through a lot of work, we found out that the iron atom retains the 3d6 configuration that you are used to from iron in the periodic table. And if you look at what this really means, that means that you have a spin of 2, which is what you used to maybe, but you also have an orbital angular momentum L of 2. And this orbital angular momentum gives rise to very strong magnetic anisotropy. So here's a picture of this particular surface. If we zoom in, 5 nanometer square image, you only see here 1, 2, 3, 4, 5 atoms. They're all identical. They're all iron atoms on a double layer of MgO. Now, if we look at what happens with the energy state, so we have at the lowest energy, we have 5 energy levels, which is the energy levels corresponding to the spin of 2, but they are not all degenerate at zero magnetic field, as they would be for a free atom, because they interact with the negative and positive charges around them. we have a very large out of plane in this direction, easy axis magnetic anisotropy, meaning that the spin is either pointing up here or pointing down here. Those are two degenerate states at zero magnetic field. And if you want to flip the spin to go from this state to one that is slightly tilted, so has SZ plus 1 instead of SZ plus 2, you have to pay 14 millielectron volts. So very, very high energy to flip that spin. Right? And we can see this energy directly as a clear step in the conductance spectrum. So here we are measuring dIdV as a function of the voltage that we apply between tip and sample. And you see we get a very clear step at plus or minus 14 millivolts, which corresponds to this excitation from the ground state to the first excited state. So this agrees with a easy axis magnetic anisotropy of a spin of 2. Now then, if we can apply a magnetic field, for example, in the out of plane direction, so if this field is aligned with the easy axis of the magnetic anisotropy, then we can split that spin and we can make an energy difference between these two states, which is proportional to the external magnetic field, and of course then contains a G factor. I note also here that if we have a perpendicular magnetic field, then we do not see any effect of this magnetic field because we have such a strong out of plane magnetic anisotropy. So that's a little bit strange for those people not familiar with magnetic anisotropy. Okay, so why do we see a step here? This goes to an effect that is due to inelastic electron tunneling spectroscopy, and it's actually relatively easy to understand. So in an STM, we have our tip, which is a metal, and we have our sample, which in this case is also a metal. And in between, we have a vacuum tunnel barrier. If I now apply a bias voltage between tip and sample, I shift the relative energy of the Fermi energies. For example, I lower the sample Fermi energy, and my tunneling current can flow anywhere in this gap from the filled states of the tip into the empty states on the sample. This gives rise to a certain conductance. Now, something happens when the energy matches the energy difference between the ground state and the first excited state of the spin system, because then the electrons can lose energy in the tunneling process and kick the spin from the ground state to the excited state. And this generally changes your conductance. In this case, in particular, it increases your conductance. That's the plus minus 14 millivolts. And then as we further increase the voltage, all the electrons can do this. And our conductance now consists of the elastic conductance plus the inelastic conductance. This is generally symmetric about zero bias. So it's characteristic of an inelastic tunneling spectroscopy and is broadened by 5.5 kT. So this is the concept of spin excitation spectroscopy, which we introduced now, what is this, 16 years ago or so, to look at the energy levels of individual spins on surfaces. And so spin excitation spectroscopy, as I said, has been around for a long time, and I don't want to spend more time on this here. It can be used to measure the Zeeman energy. If you don't have any magnetic anisotropy, for example, you can measure the magnetic anisotropy, as in this example here, of an iron atom on MgO. If this spin interacts strongly with the conduction electrons below here, if this interaction is strong, then you get a Kondo effect. Lots of beautiful work can be done here. But I think what makes the STM particularly beautiful instrument is that we can combine this with atom manipulation, and we can build structures like, for example, here, the spin ladder, where we have 6 iron atoms on a different surface interacting strongly in this direction, but only weakly in this direction. And so then you can decide to make spin structures of basically arbitrary complexity and study their properties one atom at a time. So this is, I think, the beauty of scanning tunneling microscopy. Okay, so that's kind of the introduction to just STM on these spins on surfaces. And for the rest of this talk, I want to talk about dynamic effects. So what happens with time-resolved measurements here. And so there's 2 different time-resolved domains. There is the incoherent and the coherent domain. And let me just for one slide talk about the incoherent processes. For example, you can ask yourself, how long does a spin live if I put this in the state 2? Or you can see if I put this in the state 1, it might live a long time because it's on the opposite side of an energy barrier. And then I can look at this relaxation path here. And in our common language, we call this an energy relaxation time or a T1 time. And so we can measure this T1 time without going into too many details. We can do a pump probe technique where we apply a relatively high voltage for a short period of time, and we call this the pump pulse. And during this pump pulse, we kick the system from the ground state, state 0, into all the excited states. Then we turn the voltage off and we wait for a certain amount of time. And after that waiting time, we turn the voltage back on. Let's say we put it on a smaller voltage, and we call this the probe pulse. And that probe pulse then measures which state is the system in after the delay time delta t. And so as we sweep this delay time, then we can get time resolved information on the system, and we can repeat this process many times to get good signal to noise. And so here's an example of this iron atom on 2 layers of MgO at a certain magnetic field, which I'm sorry, I forgot what value that is. We have a T1 time here for this state from 1 to 0 of 35 microseconds. So relatively long T1 time for this particular system, because we have to cross through the barrier. We have to go through the barrier via quantum tunneling, and that is just not very likely. If you ask yourself, on the other hand, if you are in state 2, how long does it take for this spin to come down from state 2 to state 0? That will be on the order of maybe 1 nanosecond or so, so much faster, because it doesn't have to go through an energy barrier. So this is incoherent dynamic processes. But this talk here, I want to focus more on the dynamic properties of these systems. And so let's look at the second part, which is the CW electron spin resonance for these spins on surfaces. Now, beyond next to the incoherent processes, we have the coherent processes. And those can best be described by, this is a slide I stole from Yuchong, one of my PIs. We want to now look at the superposition between 2 states, 0 and 1. And this superposition can best be described, or easiest be described on the Bloch sphere with 2 angles, theta and phi. One of them being how much state 0 and how much state 1 do I have, and the other one just being a phase between these 2 components. And there are many timescales that play an important role, and they need to be characterized each one. The first one is maybe the easiest to see, is related to the energy difference between state 0 and state 1. That is the Larmor frequency, and that gives rise to the precession of that spin around the main quantization axis. That's the Larmor frequency, which in our case will be on the order of several tens of gigahertz. The second one is the coherent manipulation rate, the Rabi frequency, also called the pi time, where you can change the state from state 0 to state 1 by coherent control, coherent manipulation. And then the last time that plays a role is the T2 time, the phase coherence time, which tells you how long the system actually remains on this Bloch sphere diagram before it decays into the incoherent superposition, incoherent state of state 0 and state 1. And so how can we do this in an STM? Now, this was a breakthrough that we achieved about 5 years ago when I was still at IBM. What we learned is that there is, of course, a very strong electric field in the tunnel junction, right? You have an STM tip that is about 1 nanometer away from the surface, and you can apply a voltage on the order of tens of millivolts to hundreds of millivolts. And so if you look at the electric field in this junction, this can be very large. And so what we learned is that we want to make this electric field time dependent. In particular, we want to apply a constant frequency of a time dependent electric field. And so all we had to do for our STM was to introduce, in addition to the DC bias, a microwave frequency, high frequency line, which we in practice do via semi-rigid coaxial cables, and apply a time-dependent voltage between tip and sample. And now if this time-dependent voltage, the frequency of this is matched to my energy difference between state 0 and state 1, my Larmor frequency, then I can do coherent manipulation, coherent transitions between the down state and the up state. And so let me show you this cartoon-wise as the probability for the system to be in the excited state. If we are at a moderately low temperature, then we're mostly in the state 0, so the probability of being in state 1 is small. But if I change my frequency and I hit the resonance frequency, then I can change this population because I can drive the system from state 0 to state 1. And the most I can do in this particular case, it's not pulsed, in CW, is I can go to 50% population. Now, this is what the spin system does, but this spin is in the reality a spin pointing in a certain spatial direction. And if I have a spin polarized detector on my tip, then the tunnel current will change depending on the relative alignment on these two spins. If they are parallel, I will have a certain current. And if I flip this one, then I will get a different current. And so my tunnel current basically will follow this population of the state 1, or the relative population of state 1 and state 0. And so my tunnel current will have a feature that can either be a peak or a dip, depending on the spin polarization of the tip, that will change with the resonance frequency. And so let's look at this. This is data taken with one of our microscopes here in Seoul last year. Here we have an ion atom on 2 layers of MgO, and we apply a relatively small magnetic field of 0.11 Tesla. And you can see that at about 12.2 gigahertz or so, we see a change. This is the y-axis here is the tunnel current. We see a change in the tunnel current at this particular frequency. And of course, now we want to change that frequency, change the magnetic field, which changes this resonance frequency linearly. It goes up as we increase the magnetic field. And of course, this is just the Zeeman energy splitting between these two levels that are degenerate at zero magnetic field, and they split out. Now, many of you are familiar with spin 1/2 system maybe, and so this magnetic field and frequency does not match well. That's because this is a spin 2 system, and so the effective G factor is much, much higher than what you're used to from a spin 1/2 system. Very happy to say that this is the world's second or third ESR-STM after the one that we built at IBM a few years ago. And so it shows that this can be done in different machines around the world. And I want to also show you an example from one of my collaborators and friends, Pietro Gambadella's group at the ETH in Zurich. They also showed last year that they can do ESR-STM for a spin 1/2 system here. That is a titanium atom also on MgO. And they go to even higher frequencies here in the range of 35 to 40 gigahertz. And they also see an ESR resonance shifting in this particular case with the external magnetic field. Also get a linear effect from the Zeeman effect. So there's now on the order of 5-6 of these machines around the world, 5-6 groups that have ESR-STM running. And we were actually going to hold a conference in April, actually later in April, which of course also had to be called off because of Corona. And so now we're all tapping in the dark, I guess. Okay. So how does an electric field drive ESR? Let me take a quick peek at the time here. Okay. How does an electric field drive ESR? What we believe is happening that either the electron cloud or the nuclear position of the atom on the surface is actually changing due to this electric field. And if we then have an inhomogeneous magnetic field on our tip, then this means in reality that we have a time-dependent magnetic field. So we're converting the time-dependent electric field into a time-dependent magnetic field on the surface. And so then you are a bit more in the traditional quote-unquote ESR regime. Okay, let me skip this. Now, a couple examples of why this is cool. So here's one of our best traces. We have here an ESR. This is again an iron atom on MgO. We have an ESR frequency here of 25.680 gigahertz, and we got a line width of 3.6 megahertz. If you just convert this line width into an energy, that is approximately 10 nanoelectron volts. And just to put this in perspective, that's 1,000 to 10,000 times better than the already pretty high energy resolution that we have in low temperature STM. And so, of course, any spin resonance does not really depend on temperature and can have a much higher energy resolution than the temperature, as many of you know. And so you can make much more sensitive detectors with this than you could with just regular spectroscopy. And so let me show you one example of this. So here's this iron atom I briefly mentioned from Pietro's group. This is an iron atom that actually has a hydrogen atom attached. Therefore, it is a spin 1/2 on the surface. But don't worry about that little detail here. What we see 3 different atoms. They look exactly the same in the STM picture. The blue one, what is this orange one, and the yellow one. Yet the ESR spectrum looks totally different. The blue one has only a single ESR line. The orange one has 6 ESR lines, and the yellow one has 8 ESR lines. Now, why is that? That's because there's, of course, nuclear spin around. And we have here, most of the titanium atoms are nuclear spin free. They have nuclear spin 0. We have the isotope with 47 titanium, which has nuclear spin 5.5, and 49 titanium, which has nuclear spin 7.5. And of course, with an STM, we're always looking at a single atom. And so for us, it is totally normal that we see one or the other. But all the other people, not all the people, but the vast majority of ESR spectroscopists, of course, are used to ensemble measurements. And so they always see all the isotopes mixed together in their spectrum. So they are very excited about the fact that we can do one isotope at a time. And the STM allows you to do even more. If we look at the fact that here's just a zoom in into this hyperfine interaction, the interaction between the electron spin and the nuclear spin. And you see if we are on this particular binding site here, which we call the bridge binding site, so we're not sitting on an oxygen, we're sitting in between 2 oxygens and 2 magnesiums, then we have a certain amount of hyperfine interaction. If we now move the atom on top of the oxygen binding site, we have a very different amount of hyperfine interaction, much smaller hyperfine interaction. And if we move it back to the next binding site, and of course we go back. And so from this, we can learn that the hyperfine interaction is not something that's built into, let's say, an iron atom. It is something that is probing the local environment, which is why spectroscopists like the hyperfine interaction to measure something about the local environment of their spins. So this is why ESR-STM is an important and cool tool. Now, in the end, let me go towards the pulsed measurements. So far, I've talked about CW ESR. In pulsed measurements, we now want to make a short microwave pulse, and then turn the microwave off, and then measure the state that we have, and maybe control the system coherently. And the simplest one of that is just turn on a microwave pulse for a certain amount of time, which is the Rabi oscillation, and look what happens. So for this, we have to now control our microwave generator also with nanosecond long pulses, which we do with an AWG, and the rest is not so important right now. And so here's an example of such a Rabi oscillation for a titanium atom with a hydrogen that is a spin 1/2 on MgO. We apply for us a relatively large RF voltage here of 190 millivolts. So that's 190 millivolts between the tip and the sample, oscillating at 22.57 gigahertz. And what happens here is that the spin coherently rotates between the initial state 0, excited state 1, and going back to state 0, and so on, as the system is driven here by this microwave pulse. If we reduce the amplitude of the microwave pulse, but we stay at 22.57 gigahertz, then it takes longer to make this rotation. If we reduce it more, it takes longer and longer. And you can see that at the lowest one that we've measured here, it takes maybe on the order of 100 nanoseconds to flip that spin. Now, what we see here, we see the decay of the system, of the spin here. That is the T2 Rabi time. That is on the order of 40 nanoseconds here, and it takes us to make a pi pulse approximately 20 nanoseconds at this maximum RF voltage that we can apply. Now, this means that we can do about 2 rotations of our spin in the T2 time. But the Rabi is not the only one that you can make, and as many of you can do. No, you can do better. For example, you can do an echo measurement, as cutely illustrated here by the rabbit and the turtle. Do an erase. If you do a race and then you tell them to run back, then as they come back, they will arrive at the goal line at the same time, no matter how fast they're running individually. And so this is true for spins also, and this is the famous spin echo sequence. So we take now a pi/2 pulse, so we rotate the spin from the ground state into the XY plane. We let it evolve on this XY plane, and now in our case, we do a time ensemble average. They will dephase over time. And the pi pulse, though, can flip them back and then invert this dynamic that we don't like, and we come back to the echo sequence after this pulse sequence. So this is the spin echo sequence, and in our particular case here, the T2 echo time is much longer than the Rabi or the Ramsey time, in our case, approximately 5 times longer, goes up to 190 plus minus 23 nanoseconds here. And so now we have on the order of 10 to 20 pi pulses that we can make in a T2 time, and this gets us a little bit closer towards quantum coherent manipulation of these spins. Okay, let me summarize. So I told you a little bit about my center and also the definition of what is quantum nanoscience. We then introduced electron spin resonance in an STM. First papers are coming out with this technique with data measured here in Korea. I'm very happy about that. And we can do coherent manipulation of individual spins on surfaces, which was published last October. Now, as a little bit of an outlook, we like to think that we're working on the foundations for future quantum technologies. And here's one that I've been thinking about for quite a long time. Imagine that you have a spin on the surface that actually is coherent enough to be a quantum bit, a qubit. Then with an STM, we can place them at various distances from each other, have them interact with each other. And if we can control qubit 1, 2, and 3 independently from each other, then we might have a very interesting system for small scale quantum algorithms. So this is something that we're hoping to achieve in the next 2-3 years or so. Okay, finally, I want to give you 1 or 2 slides on where we are. I'm now working at Ewha Women's University, which is one of the oldest universities in Korea, founded 1886, still in the dynasty time in the old days. Nowadays, it's a beautiful campus in the heart of Seoul. I invite you all to come and visit us. A great mixture of old and new. We have about 23,000 students. Everybody who gets a degree from our university has to be female, but we have many visiting male students as well, of course. And the funding for my center comes from the Institute for Basic Science, IBS, whose vision is to make discoveries for humanity and society. On the timeline, it's about a 10-year-old organization, and so they want to become a world leader. In typical Korean fashion, that should take about 5 years or so. And now you can't laugh, or you can laugh, I can't hear you, but that's okay. But what I really like about this IBS system, it has a relatively large-scale research effort. We have quite a bit of autonomy over our budgets and our research targets, but it is very heavily reviewed, and so I think it's a good mix for basic science. There is about 30 of these IBS centers all over Korea, and we are here in Seoul, and Incheon is right here, which is the international airport in Korea. So very easy to get to us. Once Corona allows travel again, I invite you all to come visit us in Seoul. And with this, I would like to advertise that we have positions available. If you're interested to work on exciting ESR-STM or other aspects, please feel free to contact me. My email is down here. And I want to thank my former co-workers, Chris Lutz, Kai Yang, and Bruce Mellior at IBM, with whom we have lots of collaborations, and just been a fantastic time there. Thank you very much for your kind attention.
All right, thank you, Andreas, for a very exciting talk. And probably you can hear us all clapping. And so if you want to clap at home and make it also known to Andreas, then go down, there's a reactions, and you can click on your clapping button, and he will hear that. All right, thank you very much. So the floor is now open for questions. And if you have questions, then you can find another button, which is raise your hand, or there is also a chat function where you can ask a question and we'll unmute you. So any questions? I guess everyone is searching for the correct button here. There's a chat. Say again? So we can unmute him. So Yutaka has a question, and Amit is now giving you the podium.
Okay, so
you can go ahead.
Yeah, may I have a question?
Yes.
It does. I have a can you hear me?
Yes.
Yes.
Okay, good. Thank you so much for that nice talk. In that, I have a question on the first paper on ESR-STM result. You showed that in the different in the magnetic field, in that magnetic field strength result, in that's the slightly, so the ESR peak, is that a slightly asymmetric result? Is there sort of any reason on that?
Yes.
On,
yes. So it took us quite a little bit of time to figure out why these peaks are sometimes asymmetric. And it turns out that we have two different detection mechanisms that play a role here. One is the mechanism that I sort of introduced, which is just saying that we're measuring with a spin polarized tip the amount of spin polarized tunnel current in sort of a DC fashion. But we now know that we, in addition to this mechanism, have a more time-dependent mechanism where the spin rotation of the spin on the tip is matched to the spin rotation on the spin on the surface. And with that, we can get a more dynamic measurement process. And these two processes happen at the same time and give rise to this asymmetric line shape that you can see. So, you know, it's not a trivial thing to explain hand waving, but it is well understood.
All right, thank you, Yutaka. There's a question, Andreas, from Daniel Dilevich in the Weizmann Institute of Science, and he's asking, what do you believe is responsible for the decay in the Rabi oscillations? That is, what is limiting what we call T1 row or the decay of the Rabi? Thank you.
So in the end, we are suffering a little bit from the fact that we always have conduction electrons around. And we have two sources of these electrons. One is the tunneling electrons that are flowing between tip and sample. And of course, we have to have tunneling electrons. Otherwise, we wouldn't be using a tunneling microscope. So that's one. But we also have the electrons in the silver underneath the MGO. And those electrons in the silver can tunnel through the MGO and talk to the spin on that surface and give rise to decoherence. And basically what we found is that every electron that is interacting with this spin gives rise to a decoherence event. And so in the T2, in the spin echo T2 time, the 180 nanosecond, that we believe is then limited by these electrons that are still in the process in the system. And so we would have to reduce the number of electrons by reducing the tunnel current and by making thicker insulators, which is of course something that we're working on, but we haven't succeeded yet.
All right, there's a question from Hengyun Shu from Harvard, and he's asking if you could please elaborate a bit more on how to individually control several different atoms in the system.
So the answer is we haven't done this yet, so I can't really know how to do this, but the idea that we have in mind is to simply make them have slightly different resonance frequencies and then do this by frequency control. So make sure that spin 1 and spin 2 have a resonance frequency that is slightly different, either by choosing different spins, different atoms, or by controlling their environment, by putting another atom nearby, and therefore give them different frequencies. And then we can do kind of what NMR quantum computing did, or still does, is do multi-frequency techniques. So that's the simplest way that we're thinking of doing that.
All right, Andreas, here is Christian again. I just have a brief follow-up question. So I think you control your ESR through your tip. So if there were other atoms which are far away from your tip, how would you create the RF field for those spins that don't feel the tip field?
So at the moment, we're using the electric field between tip and sample. And as you can imagine, the electric field between tip and sample is much bigger than just the apex atom that we're using for scanning tunneling microscopy for the high spatial resolution. Right? So it doesn't have to be limited to a single atom. It can be something that it may be on the order of tens of nanometers or so. And so the best I think you can do with this kind of approach is maybe control five or so spins, right? But nothing is preventing us, I guess, from using a microwave line or a particular sample that is designed that you can have a microwave current running through the sample. And then you could control more spins that are further away from your STM tip. But I think, you know, this is not going to be something where we can compete with 1,000 qubits or something like that, right? That's not the goal. The goal here is to maybe come up with something that combines this beauty of STM atom manipulation with this coherence that we get now in these spin systems, right? And so I think if we can do 5 or 10 spins, I'd be super happy anyhow.
Very nice. I'm going to hand over to Amit, who has another question.
So this will be the last question for this session, as we're about to get to the 10 minutes before the next talk. And this is a question from Aaron Blank from the Technion, Israel Institute of Technology. And he's asking, what is the difference between this method and the original ESR-STM papers using noise signal by Ishai Manassen and Durkin?
The difference really is exactly that, right? I mean, we are actively driving the spins, whereas in the original papers, they were trying to measure the noise. And, that's perfectly reasonable thing to do. I mean, there are complementary measurement approaches, and I really think that one should try to do both in the same system. I think the main difference is that this particular approach that we're doing is more reproducible because we're doing it at low temperature in ultra high vacuum environment. We can measure on the same atom for many, many days, right? So you have a large amount of data taking on one particular system, whereas most of the original work was done at room temperature, and room temperature STM sounds very good, but it's much more difficult because things drift around and it's more difficult to do long-term reproducible measurements. Right? So I think the noise measurements are great. And this, I mentioned briefly that we have this time-dependent measurement process. It's like a homodyne detection mechanism that is really closely related to these noise measurements. And so I think there's definitely something that should be done and can be done to combine these measurements together maybe.
All right, so thank you, Andreas. Thank you for answering this question, and thank you for this wonderful talk.
Yeah, a bit more clapping here.
Thank you, guys.
So I'm happy to announce that we have already 127 participants. So again, Andreas, thank you very much. And we'll start the next talk sharply at around hour, which will be 4 o'clock Israel time. It's in about 9 minutes. And the next talk will be given by Rafi Budakian from the University of Waterloo in Canada. So stay tuned. Now is the time for a break. Chocolate, coffee, restroom, whatever. Take your time. Be back sharply at 4 o'clock.